Hello, BC Calculus students. This is Mr. Johnson, and this is section 2.8. This is the last section in chapter 2, and it really introduces the idea of the derivative. I know that chapter 2 is on limits, but with our curriculum, our textbook, we end up introducing the ideas behind a derivative and an antiderivative within chapter 2. So this is the last section, and what I'm going to do first, and if you want to write this down, you can certainly go to the back of your booklet, which has some blank pages starting at page 74. But I'm going to provide just a little chart for you that will help you organize the function, the first and second derivatives. So let's say that we have some different characteristics of the first derivative, and we're trying to analyze what does that tell you about the function itself. So first off, what if you have a derivative that is positive? Well, that tells you that the function is going to be increasing for that interval. If your first derivative is negative, then your function is decreasing. And I know you've seen all of that last year, but again, this is just a review of all that material. Let's say that the first derivative changes from positive to negative. Well, then the function then would have a relative maximum. And let's say that the first derivative changes from negative to positive. Well, then the function would have a relative minimum. Okay, so usually with the first derivative, we're in pretty decent shape. You guys have all seen it before, and you know it's something that you've done since really early on last year. Then we want to introduce the second derivative, and again, you've all seen this, but the second derivative is now the next layer of what we're trying to analyze. So if, let's say, the second derivative is positive, what does that tell you about the graph of f? Well, for f, it would be concave up. But we also want to discuss what happens to the derivative then, because the second derivative is now obviously the first derivative of the first derivative of f. So in other words, it tells you that f prime is going to be increasing, because again, it's that similar layer between f and f prime as f prime is to f double prime. Let's say that our second derivative is less than 0. Well, then we have a graph of f that is concave down and a decreasing first derivative. Okay, let's say that we have a second derivative that changes from, let's just do positive to negative. Now with the graph of f, positive means concave up, negative means concave down, and so this would be a point of inflection where the concavity would change. And the second derivative may be 0, it may be undefined. We'll talk more about that a little later. The first derivative would have a relative maximum. And then let's say that the second derivative changes from negative to positive. Well, then our function, again, has a point of inflection because you change from concave down to concave up, and the derivative would have a relative minimum. Now, we could obviously continue this. We could go to the third derivative. We could say, okay, what does the third derivative tell you about the second derivative and the first derivative and so on? We could go through this chart, and what you'll see is that this current pattern that we're on is just going to continue depending on which derivative level we're on. So AP is really good at starting to test you on, okay, let's say that you have a function that's the third derivative. What does that tell you about the first derivative? And so you want to think about the layers of your derivatives and how far apart they are from the function that you're trying to analyze. So let's take a look at some of our examples in our notes. Let's just say that this particular graph is f prime of x, and we're trying to figure out if this is f prime of x, what does it tell you about the original function f of x? So first off, f prime of x is greater than 0 on the interval from a to b, and therefore f of x is increasing during that time. The derivative f prime is less than 0 from b to c, and therefore f of x is decreasing during that interval. The function f prime is equal to 0, and it appears as though it's changing from positive to negative at x is equal to b. Therefore, f of x has a relative maximum. Okay, so that's kind of what we take from this. We also see that at letter C for x, it appears as though the first derivative is 0. We don't know if that means that maybe there's another relative value for f of x. We don't have any information beyond C, so therefore we have to kind of pause and say, okay, this is about what we can take from the graph of f prime. All right, now let's go ahead and discuss the next one. And this time, I know it's the exact same graph, but let's just pretend like this particular graph is f double prime now, just so that we can pull some information out of it. So if we look at the first part, f double prime is greater than 0 on the interval from a to b, and that would mean that f of x is concave up. It also means that f prime is increasing. And then we can see that f double prime is less than 0 from b to c, and that would mean that f is concave down and f prime is decreasing. Okay, we can see that f double prime is equal to 0 at b, and it changes from positive to negative. So that means that f of x has a point of inflection. It changes from concave up to concave down, and f prime has a relative maximum. All right, so again, this is some of the interaction between a function, a derivative, and its second derivative, and I hope some of that makes some sense. But the more that we practice with these concepts, the more that we look at different graphs or equations or characteristics of each, the better we can do when it comes to identifying what the first derivative or the second derivative say about the function f. All right, let's go to the next page. I mentioned points of inflection, but just to reiterate, inflection points will occur when the second derivative is either equal to 0 or when it's undefined, and we want to make sure that it changes signs. So again, it cannot just simply be 0 and be a point of inflection, because a graph could be concave up and then it could sort of have a second derivative equal to 0. It could sort of pause and then it continue concave up. So you must have a change of signs of the second derivative in order to have a point of inflection. And then again, a little bit as an extension here in terms of antiderivatives, how do you know a function is an antiderivative? The easiest way to know is to test the derivative. What I mean by that is, let's say that you have the integral of x squared dx, and you think the antiderivative is 1/3 x cubed plus c. So the way you can test this is you can take the derivative of 1/3 x cubed plus c, and if you do that, it's the power rule, so you bring the 3 down, that cancels with the 1/3, and you get x squared, and the derivative of c is 0, and you're able to double check that you have the correct antiderivative. So taking the derivative allows you to test whether or not the antiderivative is accurate. All right, let's try some examples. So our first example is that we have the graph of f of x, and we're trying to figure out on which of the following intervals is the function increasing. So what are we looking for? That kind of goes back to that chart we did at the beginning. So we're looking for when the derivative is greater than 0. So let's first find the derivative using the power rule. So we have f prime of x is equal to 300 minus 3x squared. Probably helps us to factor this. And then we want to identify when the first derivative is positive, so we're going to set it equal to 0. So we have 0 equals the first derivative, and if we solve for x, we get plus or minus 10. We can put this on a test line, and again, what we're doing is we're testing the sign of the first derivative to make sure that that sign is greater than 0. Now, one of the ways that I do this, if I can, is I take a look at the first derivative, which is 300 minus 3x squared. I know that looks like a parabola that is opening downward, and what I just found are the x-intercepts of that parabola. So if I'm able to think about the first derivative as a little sketch, I can immediately determine that it's negative on this interval, positive on this interval, and negative on that interval, and I don't have to test any points. Now, if you want to test negative 11 and plug it in and see if it's positive or negative, and then plug in 0 and then plug in 11 or whatever. If you want to pick a point on those intervals and test your derivative, that's fine. Doing a sketch saves you tons of time if it's a possibility. Sometimes the equation is too difficult to sketch, but many times you can sketch it. So here we can see immediately that the portion of the first derivative that is positive, making f increase, is the interval from -10 to 10, which is option B. All right, here's our next example. We have a function g, and k is a constant, and we want to know what value of k does g have a critical point at x equals 2/3. So we didn't talk about critical points yet or review those, but critical points occur when the first derivative is either equal to 0 or undefined. And so we're going to first start with our derivative of g. And by the way, I made this generic to f. Fill in the blank, whatever function you have there. So in this case, I have the derivative of g, which is 2x e to the kx plus x squared times k, because of the chain rule, e to the kx. Now, what we're going to do is set this equal to 0. We know that all of these values are defined, x, 2x and x squared, those are polynomials. E is a continuous function, so we know the derivative that it exists everywhere, but we want to know when is it equal to 0, and we want to solve this, so we want to factor out as much as we can in order to get something that's a little bit more simple here. Now remember, the critical point exists when x is 2/3, so this portion of the equation is really impossible to equal 0 if x is equal to 2/3. So what we're focused on here is the equation 2 plus x k equal to 0, because again, that defines a critical point, but we're just going to go ahead and substitute in 2/3 for x. So what we have is 2 plus 2/3 times k equal to 0, and if we just simply solve this, solve this for k will equal -3, which is option A. Okay, let's go to the next page. All right, this is a pretty fast page here because we're just doing one problem. You've seen numerous problems like this. One of the things that I want to briefly review with you is the fundamental theorem of calculus. We consider it part 2. Some textbooks consider it part 1. What it says is that if you have a function f of x equal to the integral from a constant value a to x of, let's just use what they have here, g of t dt, okay? If you're going to take the derivative of that, it's really the derivative of the integral with a variable upper limit. And we'll be going through this in class, showing you the kind of the full proof or sort of a demonstration of it. But this is simply just g of that upper variable limit of x. If you had, let's say, f of x equal to the integral from a to, I don't know, like sine of x gt dt, then your derivative, if you're calculating f prime, is going to be g of sine of x, but because of the chain rule, you have to multiply by the derivative of what you just input, because you created this composite function, and so you'd have to multiply by derivative of sine, which is cosine. Okay, with that all being said, we're not doing the second part. What we're doing here is the first part. So what we're actually being told from this piece of information here is that the derivative of f is equal to g of x. So when the question says the figure above shows the graph of f, which of the following could be the graph of g? What is actually asking for is which of the following could be the graph of the derivative of f. They're just communicating in a different way. So if we were to look at our graph of f up here, we're trying to find the derivative, which is a fancy way of saying find the slope. We don't have any labels here, but what we can see is that f is linear. And if f is linear, that means there's a constant slope, which means the derivative is constant. And f is increasing, which means that the derivative must be positive. So maybe the slope is 2, or maybe the slope is 1 or 3, and it would look something like option A. Okay, let's go to the next page. Okay, a couple other examples to go over. So we have g, and it's a function with the first derivative defined above. Which of the following must be true on the interval 0 to 2? So we're actually going to use the fundamental theorem part 2 again, because the second derivative is the derivative of this integral with a variable upper limit, and we simply just substitute in and we get a derivative equal to e to the power of negative x squared. Now if you think about plugging in values, so you're substituting in values for x, and what I'm doing is I'm focusing on the second derivative right now. So if we're substituting in values for x, where we're looking at x in between 0 and 2, no matter the value we put in, e to the negative x squared is going to be greater than 0. There's nothing we could substitute in to make it either 0 or negative. Let's go over and look at the derivative as well. So we have the derivative, this integral, and we got to think about what this integral gives us. So the integral, remember, is the area from the curve to the x-axis. So e to the negative t squared, since, and we just discussed this, since this function is positive, since it's above the x-axis, if we're to calculate the area from 0 to somewhere up to 2, not including 2, then we're actually totaling up positive area, which means the derivative also is positive. So we have a positive first derivative, we have a positive second derivative, and that tells us that the graph of g is both increasing and concave up. Okay, example 5, we have the graph of f prime, which is the derivative of f. Which of the following statements must be true? So f has a relative minimum at -3. And again, remember, we're kind of going back to that chart we did at the beginning of this section. So what happens when f has a relative minimum? You may even want to page over and look at that. The first derivative must change from negative to positive. And in this case, in this graph, the first derivative is below the x-axis, therefore it's negative. And then it's above the x-axis, so therefore it's positive. So this derivative, in fact, does change from negative to positive, which means that is a relative minimum. So option 1 is true. Option 2, the graph of f has a point of inflection at -2. So we're trying to analyze, basically, what is happening right here on the graph of f. Is it a point of inflection? The answer is false, it is not, and I think what they're trying to do is they're trying to trick you, because it is a point of inflection on the graph of f prime, but it is not a point of inflection on the graph of f, because remember, the point of inflection on the graph of f occurs when the second derivative is either 0 or undefined and changes signs. And right now, if you look at the graph of f prime, it is increasing throughout this section, which means that f double prime is positive, which means that over this little area here, or this spot of x, f is going to be concave up. It's not going to be a point of inflection. And then the third one says that the graph of f is concave down from 0 to 4. So if we were to analyze basically anything, let's see, 0 to 4, anything here, the question is f concave down? Well, the first derivative is positive right here, and then the first derivative is negative right there. But remember, the first derivative doesn't tell you whether or not f is concave up or down. The second derivative tells you that. So over the entire interval, the first derivative is decreasing. And remember, when the first derivative decreases, that implies that the second derivative is less than 0, which means that f is concave down. So that is also true. So what we have for an answer is letter E. Okay, last page, last example. All right, in our last example, we have the graph of f shown above. For which of the following values of x is f prime positive and increasing? So f prime being greater than 0 means that f is increasing. Again, think back to that chart we did at the beginning of the section. F prime increasing means that f double prime is positive, which means that f is concave up. Okay, so what we have are 5 options here, And we're focused right here on option E because F is increasing and F is concave up. And that is the last example for not only our section 2.8, but also our chapter 2 as well. So congratulations for finishing this chapter. And we will now try to finish it up by doing the examples, and then we'll move on to chapter 3. Thanks.